Hi everybody, welcome back to Beginning Algebra. Today we're in section 6.5 and we're going to be talking about special factoring techniques. So in this section we're looking at expressions that get factored pretty much by a particular rule or formula, not by trial and error or by reverse FOIL the way we saw in the previous sections. Today we're looking at difference of squares and sum of cubes and difference of cubes. And I'll show you the pattern for each of these. Okay, first remember from chapter 5 that multiplying together a sum and difference of two terms produces a difference of squares. And that means that if we want to factor a difference of squares, what we have to do is just put it back in its form of a sum and difference of two terms. So in chapter 5, we learned how to take a multiplication problem like this and multiply these two binomials together to get this. And remember, when we would do that, the outer and the inner would cancel out and would just leave us with two terms. Well, in this section we're going backwards. We're going to start with this form and we want to learn to put it back into this factored form where we've got a sum and difference of the same two terms. Now remember, the word difference means subtraction. So this is a difference of two squares. A difference of squares has to be square minus square. And it's a very common mistake for people to make to try to factor a problem that says x squared plus y squared. But that's not a difference of squares because difference means subtraction. So let's try factoring each of these binomials. And the first thing we need to do in each case is verify that we are looking at a difference of squares. So do I have here square minus square? Yes, of course, p squared is a square. This is a minus sign. And 16 is a square because that's 4 times 4. So to factor this, we would put down two pairs of parentheses. P squared needs to be broken down into p times p, and then we're going to have opposite signs here. 16 is 4 times 4, so this parentheses can be minus 4 and the other one can be plus 4. It does not matter what order you put these in as long as you get them both in there. So we could have written p plus 4 times p minus 4, that would also be correct. But this is the factoring that we were after, p minus 4 times p plus 4. Okay, now let's try x squared minus 8. Remember, first you have to look at it and make sure that it's a difference of squares. So here I have square minus, 8 is not a square. There is no whole number that I can multiply times itself and get 8. So this is not a difference of squares. And therefore, this binomial is prime. It cannot be factored. And now let's look at part C. Here we have p squared plus 16. Now this is not a difference of squares either because remember, difference of squares means we have to have square minus square, but this is a plus. So this is also going to be prime because that expression is not a difference of squares. Now, although part C is not a difference of squares, it does have a name. Plus means sum. So this is a sum of squares. And a sum of squares with no GCF cannot be factored using real numbers. In other words, if we had a GCF here, we could at least factor that out. But a sum of squares is never going to factor, so the sum of squares is always going to be prime. Now here are a few for you to practice on. So I hope you'll pause the video and try these yourself. And now I'm going to go through them with you. Remember, your first step is you need to make sure that what you've got is a difference of squares. So looking at part A, we have y squared minus 10. This is square minus 10, but 10 is not a square. So this is prime because this is not a difference of squares. Now let's look at part B. Here we have 3x squared plus 12. Well, I do see a GCF here. So I'm going to factor out the GCF, which is 3. 3 goes into both of these numbers. So if I undistribute the 3, I'll have 3 times x squared plus 4. Notice that if I distribute the 3, I get this form back. Okay, so this is the correct factored form. But now we need to try to factor the x squared plus 4. But notice that we have a plus here. So this is a square plus a square, and that means that this is a sum of squares, so this cannot be factored further. Now, a lot of students here are tempted to write the word prime out here. But this is not a prime problem. Prime means I'm not able to do any factoring. But we did do some factoring. This has been factored, so it's not prime. So if you wrote prime here, it would be like saying, I'm broke, and then pulling $2 out of your pocket. You're not broke, you got $2. So this is not prime, but we just will not be able to do this last factoring step that we might have expected to do. Okay, now look at part C. P squared minus 100. And this is a difference of squares because we have square minus square. 100 is 10 squared. So that means we're going to be able to factor this into a sum and difference of the same two terms. P squared will give us P times P, and then minus 100 will give us minus 10 and plus 10. And that is how we factor that difference of squares. These other two, parts A and B, were not a difference of squares after all. A was prime and B was not prime because we were able to get a GCF out of it, but we just weren't able to factor it as a difference of squares. Here are a few more to look at. So let's look at these together. Here we have 25m squared minus 4. So 25m squared is a square. 5m times 5m would make 25m squared. And then we have the minus that we have to have. And then we have 4. And 4 is 2 times 2. So this is a difference of squares. And we're going to be able to factor it into a sum and difference of the same two terms. 25m squared is given by 5m times 5m. And then negative 4 could be given by negative 2 times positive 2. And notice that if you were to apply the FOIL method to multiply these two together, it would go back to this form. So this is the factored form. And you do have to have 2 and 2 here. Like occasionally a student will say to me, well, could I put a 1 here and a 4 here? And you cannot. And the reason you can't is that that will mess up your middle term. You need these two numbers to be the same so that outer plus inner will add up to 0. Okay, let's try part B. First, make sure that it's a difference of squares. 49z squared is going to be 7z times 7z. So that is definitely a square. Then we have our minus. And then 64 is 8 times 8. So this is a difference of squares. And we can factor it into a sum and difference of the same two terms. 49z squared is going to be 7z times 7z. And then negative 64 is going to be negative 8 times positive 8. And there is our difference of squares. And then finally we have part C. So we have 9x squared minus 4z squared. So 9x squared is 3x times 3x. 4z squared is 2z times 2z. And we do have the minus between them, so we do have a difference of two squares. So that means that we can factor into a sum and difference of two terms. So 9x squared is going to give us 3x times 3x. And then negative 4z squared is going to give us negative 2z times positive 2z. And there is our factoring for part C. Now here are a few difference of squares problems that are maybe a little more complicated than the last couple that we looked at. Let's take 81y squared minus 36. First, notice that we do have a GCF here. 81 and 36 can both be divided by 9. So the first thing we need to do is factor out the GCF 9. Now that might not be your first thought because 81 is a square, 81 is 9 times 9, and 36 is 6 times 6. So your first thought might be, oh, I've got a difference of squares. But you just have to train yourself to look for a GCF before you get started. 9 goes into both of these numbers. So let's factor out the 9. 9 times 9y squared would make 81y squared. And then 9 times negative 4 would make negative 36. So here we are first pulling out the GCF of 9. Now notice that what's left in parentheses is a difference of squares because 9y squared is 3y times 3y. And 4, of course, is 2 times 2. So when we factor this difference of squares, we're going to still keep our GCF out here. but we're going to have two empty pairs of parentheses. 9y squared is going to be 3y times 3y, and then negative 4 is going to be minus 2 and plus 2. Now, I just want to show you what would happen if you factored this as it stands without factoring out the GCF first. You could write 81y squared is 9y times 9y, and 36 is 6 times 6. You could do that, and it's not that it's a wrong step, it's just that you can't stop here, and everybody wants to stop here. But this problem would not be finished, because notice that the first parenthesis contains a GCF. 3 goes into both of these numbers. So you're obligated to factor out that 3, and you're obligated to factor a 3 out from this one as well. And if you do that, this is what you'll get. So I'm just saying I would not do this because it leads to an answer that's not fully factored. The best thing is for you to get in the habit of factoring out your GCF first, and that will be more likely to lead you to the right answer in the smallest number of steps. Now let's look at part B. Here in part B we have p to the 4th minus 36. Now there's not a GCF here, and this is still a difference of squares because p to the 4th is p squared times p squared, so we can still factor this as a difference of squares. P to the 4th is going to be p squared times p squared like I said, and then minus 36 is going to be minus 6 and plus 6. Now whenever you have a fourth power problem that you're trying to factor, always look at your answer and see if your answer contains a difference of squares. So here I have a difference, but it's p squared minus 6, and 6 is not a square, so this cannot be factored more. And this cannot be factored either because this is a sum, so it's not going to factor at all. And this is as far as we can go with this problem, so that's fully factored. Now let's look at part C. Here we have m to the 4th minus 16. So again, it's a fourth power problem just like part B was, and we have square minus square, so we are going to be able to factor this. M to the 4th is going to be m squared times m squared. The 16 is going to be negative 4 times positive 4. And see, that way negative 4 times positive 4 gives us negative 16. So this works great. But notice that in this case, our final answer does contain a difference of squares. Here we have a minus sign, so we have square minus square. 4 is 2 squared. So we need to factor this. This is going to make two binomials, and we also need to not lose this. So I'm going to copy down two empty sets of parentheses to factor this in, and I'm also going to remember not to lose that m squared plus 4 at the end. So m squared is going to be m times m. The minus 4 is going to be minus 2 times positive 2. And then don't forget you still need your m squared plus 4 down here. And now this is fully factored. So just one final reminder here. Remember, if your answer contains a difference of squares, make sure that you factor again so that the final answer does not contain a difference of squares. And it's just something you have to train yourself to do through practice. It's the same kind of thing that you went through when you were learning to work fraction problems. You had to remember to look at the answer at the end to see if it can be simplified. You have to remember to look at this answer at the end and see if it can be factored. Now let's move on from difference of squares and talk about sum of cubes and difference of cubes. They're very similar, and in fact the formulas that we use to factor these are the same except for the plus and minus signs. So first I'm going to show you the sum of cubes, and then I'll show you how to adapt that for the difference of cubes. So a sum of cubes is an expression that has the form cube plus cube. So third power plus third power. So the plus is where we get the word sum, and then we say sum of cubes because both ends have cubes. A difference of cubes is the same thing but with a minus sign. So cube minus cube. Now, you would never be able to factor these by trial and error. You can't do it the way we did back in section 6.2 where you just reverse FOIL. It won't work, and you'll see why when I show you the formula. It's not something anybody would ever come up with by trial and error. So to factor a sum of cubes, what you do is you figure out what is this the third power of and what is this the third power of. Whatever those numbers are, you put those here in the first parentheses. So if this is the third power of x, we put x here. If this is the third power of y, we put y here. And then we build this trinomial. And the way we build this trinomial is whatever this first term was, this x, multiply it by itself, that gives you the first term. The second term is going to be minus the first one times the second. And then the third term is going to be the second term times itself. So x squared minus xy plus y squared. I don't really want you to feel like you have to memorize this formula, although you do have to learn the pattern. So there is something to commit to memory, but I don't really want you to necessarily stress about this formula. The difference of cubes formula is very similar. If you look at it here, you can see that the x's and y's and the x squared and y squared, they're all in the same place. The only difference is that where we had a plus before, now we have a minus. And where we had a minus before, now we have a plus. But this third sign stays a plus. So I don't want you to say to yourself, change all the signs. That won't work. This third sign doesn't change. So let me show you an easy way to remember how the signs go in these two patterns. So again, you do need to memorize the patterns, and we're going to use the acronym SOAP to help us with the signs. So whenever you factor a sum of cubes or a difference of cubes, the signs are going to have to follow SOAP. And what I mean by that is S stands for same sign as the problem. O stands for opposite sign from the problem. AP stands for always positive. So the first sign in your factoring will be the same as the problem. The second sign in your factoring will be the opposite from the problem. And then the last sign will be always positive. Let's notice that here. Here's the sum of cubes pattern for us. Notice that the first sign is the same as what's in the problem. The next sign is the opposite of what's in the problem. And the third sign is always positive. And also look at the difference of cubes formula, and we see the same thing. The first sign is the same as what's in the problem. The next sign is the opposite of what's in the problem. And the last one is always positive. Now the thing about factoring sum of cubes and difference of cubes is that if you don't know the cubed powers of some of the smaller numbers, you will never recognize a sum of cubes problem when you see it. So let's just look at the third power of some of these numbers. 1 cubed, of course, is 1. 2 cubed is 2 times 2 times 2, so that's going to be 8. 3 cubed is 3 times 3 times 3, so that's 9 times 3, so that's 27. 4 cubed is 64. 5 cubed is 125. 6 cubed is 216. 7 cubed is 343. 8 cubed is 512. 9 cubed is 729. And 10 cubed is 1,000. And you need to at least be able to recognize these numbers. So when you see a problem that contains a 512 or a 343, you want to not get freaked out by that. You want to be able to just say, oh, well, I know that number is just 8 to the third power. So when you can recognize these numbers, it makes the problems a lot easier because it tells you how to approach the problem. Now let's practice factoring a difference of cubes. Here we have x to the third minus 8. So now just like when you were factoring difference of squares, the first thing you should look for when you're factoring difference of cubes is that you have a cube minus cube pattern in your problem. And so we do see that this is a third power and this is a minus. And the question is this a third power? Because if it is, we can go ahead, and if it's not, we would be stuck. But this is a third power. We know 8 is the third power of 2. So now we can go ahead with our pattern. And the pattern for factoring a difference of cubes or a sum of cubes is first to put a binomial-sized pair of parentheses and then a trinomial-sized pair of parentheses. So I need 2 terms to fit in here, and I need 3 terms to fit in here. And the way to get the first 2 terms is you say, what is this the third power of? Well, this is the third power of x. So x is going to go here. And then remember SOAP, same, opposite, then always positive. So this sign needs to be the same as what's in the problem, so that's a minus. And then, what is 8 the third power of? 8 is the third power of 2, so we're going to put a 2 here. Now for the trinomial, the way to get these next three terms is you do this term times itself. So x times x would be x squared. That's going to go here. And then opposite from what's in the problem. The problem had a minus. That means I need a plus here. The middle term we get by multiplying these two things together. So x times 2 would be 2x. That's going to go here. And see, you don't have to worry about this minus sign because we've already taken care of the sign by remembering SOAP. Same as the problem, opposite from the problem, always positive. And then this last number is going to be this number times itself. So 2 times 2 is 4. And this is the factoring for x cubed minus 8. Now, some students get worried about, do I need to try to factor this trinomial? And the answer is no, because this trinomial is not factorable. This trinomial is prime. So this is as far as our factoring goes. And now, just this one time, I'm going to take you through a check of this. We're going to multiply these two polynomials back together and make sure that we get x to the third minus 8. I do not want you to do this every time, but I do want to go through it with you this one time so that you can really trust the formula. So we're going to be multiplying our answer back together and see if we go back to the problem. So remember, to do this, all we do is distribute the x and then distribute the negative 2. X times x squared would be x to the third. X times 2x would be 2x squared. X times 4 would be 4x. Now distributing negative 2. Negative 2x squared would be that, so negative 2x squared. Negative 2 times 2x would be negative 4x, so that goes here. Negative 2 times 4 would be negative 8, so that goes here. And now combining like terms, you can see that the x squared and the x will add up to 0. So that's going to leave us with x cubed minus 8. And so that's why this factoring works. And now that we've done it, you can see probably that you would never come up with this by trial and error. At least I know I never would have. So you really do have to know the pattern in order to get these factored. Let's factor another one. So here we have x to the third plus 27. So first we want to make sure that we are dealing with a sum of cubes pattern. Of course, when you see x to the third, you know that's a cube. And then this is a plus, so that's a sum. And then 27, is 27 a third power? Well, yes, 27 is the third power of 3. So now we know that this is a sum of cubes, and we know that it can be factored by setting down a binomial and a trinomial. So this is the third power of x, so x goes here. And then the sign is same as the problem, S for same. And then the 27 is the third power of 3, so 3 goes here. Okay, now the trinomial is easy. After you get the binomial, the trinomial is easy. You say x times x, and that's going to be x squared, that goes here. O for opposite, so opposite of what's in the problem. And then the middle term is made of first times second. So x times 3 is 3x, that goes here. AP for always positive. And then 3 times 3 is 9, and that goes here. So here is your factoring for x cubed plus 27. I really believe that if you will practice with this pattern just a few times, this will get much easier for you. It always throws students for a loop at first. It's like learning the words to a song you don't know. You have to learn the words, but then the song is easy. So this pattern, you have to learn the pattern, but then it's easy to use once you learn it. And just one more time, we're going to check, and again, this is not something we'll do every time, but just for the sake of understanding it thoroughly, we'll check this one more time. So distributing the x, we're going to get x to the third minus 3x squared plus 9x, and then distributing the 3, we're going to get plus 3x squared minus 9x plus 27. Okay, now the two middle terms will add up to 0, and that's going to leave us with x cubed plus 27. Okay, here is example 4, and so from here out we won't check the answers anymore, but we'll just use the pattern and really trust that pattern. So for each problem, we first need to identify whether it's a difference of cubes or sum of cubes or something else. So here we have cube minus 125. Is 125 a cube? Is 125 a third power of anything? Yes, 125 is the third power of 5. So now we know that we're going to be able to factor this as a difference of cubes. So we set down our binomial and trinomial size parentheses. M to the third is the third power of m, so I'm going to put m here. Then same as in the problem, and 125 is the third power of 5, so I'm going to put 5 here. Now to build the trinomial, we say this thing times itself, so m times m is m squared, and then opposite sign of what's in the problem. The middle term is made of this times this, so m times 5 is 5m, put that here. And then AP, always positive, remember S-O-A-P. And then the last term is made of this thing times itself, so 5 times 5 is 25. And there's our factoring for m to the third minus 125. Here in part B we have 8p to the third plus 27. So first let's make sure that this is a sum of cubes. 8p to the third is going to be 2p times 2p times 2p, because 8 we know is 2 to the third. So I'm just going to write that this is 2p to the third power. 27 we know is 3 to the third power. So now we know that this is cube plus cube, so we know we can factor this as a sum of cubes. Let's set down our binomial and trinomial size parentheses. And now we say, what is this the third power of? 8p to the third is the third power of 2p. So 2p is going to go here. Same sign as in the problem. And what is this the third power of? 27 is the third power of 3. So we'll have 3 here. Now these three terms are made of these pieces. So the first term is 2p times 2p. 2p times 2p is going to be 4p squared. And then opposite sign from what's in the problem. The middle term is made of this times this. So 2p times 3 is going to be 6p. That's going to go right here. And then AP for always positive. Remember S-O-A-P. And then the last term is this term times itself. So 3 times 3 is 9. And that goes right here. Now remember, your trinomial is not going to be able to be factored, so you don't even have to stop to look at that. And this is the final form of factoring here. Let's look at part C. Here I have 4m to the third minus 32n to the third. And notice that 4 and 32 are not third powers. So this is not a difference of cubes in the form that we see it here. But notice that 4 and 32 can both be divided by 4. So that means we have a GCF. And that means we should factor out the GCF of 4. So I'm going to write 4 in front of the parentheses and then have my binomial here. 4 times m to the third would make that first term, minus 4 times 8n to the third to make that second term. So just make sure you're satisfied that if you distribute the 4, it will go back and look like this again. So we factored out the GCF of 4. Now let's see if we have a difference of cubes here. Sure enough, m to the third is the third power of m, and 8n to the third is the third power of 2n, because 2 to the third power is 8 and n to the third power is n to the third. Okay, so now we know we have a difference of cubes here. Let's keep our 4, but set down our two empty pairs of parentheses, a binomial and a trinomial size. M to the third is the third power of m, so we'll have m right here. Same sign as in the problem. And then 8n to the third is the third power of 2n, so that goes here. Now your trinomial, remember, is made out of these pieces. So now for the trinomial, we say m times m is m squared. Opposite sign from what's in the problem. For the middle term, multiply these two together. M times 2n is going to be 2mn. And then the last term is going to be positive because SOAP, we know this needs to be positive. 2n times 2n is going to be 4n squared. And there's your factoring for part C. Now here are 3 more that are kind of similar. I think if you wanted to, you could go ahead and pause the video and try each of these on your own. See if you're getting the hang of that pattern. And then when you've tried these on your own, I'll go through them with you. Okay, now I'm going to go through them with you. So we have k to the third plus 27. Let's verify that this is cube plus cube. And yes, we know 27 is 3 to the third. So I'm going to set down my 2 empty pairs of parentheses. K to the third is the third power of k. Same sign as in the problem. 27 is the third power of 3. So that goes here. Now the trinomial is going to be k squared. Opposite sign, k times 3, so that's 3k, always positive, and then 3 squared, which is 9, so that goes here. And there's our factoring. Look at part B. Here we have 8m to the third, which is the third power of 2m. And here we have 125p to the third, which is the third power of 5p. So we do have a sum of cubes here. And nothing goes into both 8 and 125, so we don't even have a GCF or anything. Let's go ahead and start our factoring. So we said that 8m to the third is the third power of 2m, and we said that 125p to the third is the third power of 5p. So this is going to be 2m plus 5p. Now your trinomial is going to be 2m times itself. 2m times 2m is 4m squared. Opposite sign. For the middle term, we do 2m times 5p. That's going to be 10mp. And then AP, always positive. And then the last term is going to be 5p times itself. So 5p times 5p is 25p squared. And there's our factoring. And now when we look at part C, 4m to the third minus 20 is not a difference of cubes because 4 is not a cube and 20 is not a cube. But I do see that we have a GCF of 4. So let's factor out the 4 and then we'll see where we are. If we factor out the 4, we'll get 4 times m cubed minus 5 because you see that 4 times m cubed will make that and 4 times minus 5 will make that. And now we need to ask ourselves, is this a difference of cubes that can be factored further? And the answer is no. 5 is not a cube. So this binomial cannot be factored any further than it already has, and we'll stop here. But please resist the temptation to write prime here because this problem is not prime because we did do some factoring. We just weren't able to do all the factoring that we might have expected to do. And that's it. So in this section, we talked about how to recognize a difference of squares, a difference of cubes, or a sum of cubes. And we've talked about how to factor each of those things. But remember, it's most important to recognize them first. And then it will be easy to factor once you've recognized what pattern you're dealing with. So that's it. You just need lots of practice to reinforce these patterns because I'm telling you, these patterns, although they're easy while you're doing them, they are going to evaporate quickly because you've not used them a lot. So you're going to find that, like, you might learn it today, but the next time you sit down to study, you've kind of forgotten how it worked and you have to refresh your memory. And you just have to keep refreshing your memory so that on test day, you have it all under control. And that's it. Good luck.